So I'd like to apologize. In the last tutorial, I had forgot to rename the tutorial to tutorial 3. Now that we're doing tutorial 4, it's going to be renamed to this. And I also forgot to increment this. So what we're going to do from here on out is shaders. In fact, everything we've done, every effect and technique will be implemented entirely in shaders. Shaders are the modern way of doing 3D graphics. In a way, you could claim that this is a step back, as most of the 3D functionality that was provided by the fixed function pipeline and required the developer to only specify configuration parameters, lighting, attributes, rotations, values, etc., must now be implemented via the developer. However, this programmatically enables some very great and superior flexibility and innovation that was incapable of being done in the fixed function pipeline. So before we begin, I would like to show you a graph. Actually, I'd like to draw you a graph of the stages of the OpenGL programmable pipeline, which we will be using. There is technically 5 stages for now, and I'm going to just draw some boxes here to show you the 3 of the little ones, the kind of the big major one, and the major one has sort of a sub stage, and I'll just connect these all with a nice line, nothing pretty. Fill this in. So the first stage we have is the vertex processor. The second stage in the pipeline is called the geometry processor. And the third stage, which is a little more complicated, is the clipper. And then probably the biggest stage is the rasterizer. And the rasterizer also has this little subsection called the fragment processor. I'll just leave that in there. So the vertex processor is in this little bit here, is in charge of executing the vertex shader on each and every vertex that passes through the pipeline, the number of which is determined according to the parameters to your draw calls. Vertex shaders have no knowledge about the topology of the rendered primitives. In addition, you cannot discard vertices in the vertex processor. Each vertex enters the vertex processor exactly once, undergoes transformations, and continues down the pipeline. The next stage is the geometry processor. In this stage, the knowledge as to the complete primitive, i.e. all of its vertices, as well as the neighboring vertices, is provided to the shader. This enables techniques that must take into account additional information beside the vertex itself. The geometry shader also has the ability to switch the output topology to a different one than the topology selected in the draw call. For example, you may supply it with a list of points and generate 2 triangles from each point, a technique known as billboarding. In addition, you may have the option to emit multiple vertices for each geometry shader invocation and thus generate multiple primitives according to the output topology you selected. The next stage in the pipeline is the clipper. This is a fixed function unit with a straightforward task. It clips the primitives to the normalized box we have seen in the previous tutorial. It also clips them to the near Z and far Z clipping planes. There is also the option to supply user clipping planes and have the clipper clip against them. The position of vertices that have survived the clipper are now mapped to the screen space coordinates, and the rasterizer renders them to the screen according to their topology. For example, in the case of the triangles, this means finding out all the points that are inside the triangle. For each point, the rasterizer invokes the fragment processor. Here you have the option to determine the color of the pixel by sampling it from a texture or using whichever technique you desire. The 3 programmable stages, vertex, geometry, and fragment processors, are optional. You don't need to bind a shader to them. Some default functionality will still be executed. Shader management is very similar to C and C++ program creation. First, you write the shader text and make it available to your program. This can be done by simply including the text in an array of characters in the source itself or by loading it from an external file. Then you compile the shader one by one of the shader objects. After that, you link the shader objects into a single program and load it onto the GPU. Linking the shader gives the driver the opportunity to trim down the shaders and optimize them accordingly. And if the shader is later paired with a fragment shader that is used, the if you you can swap them in and out on the fly, and you can even change the vertex or the fragment shader of a program on the fly. So that's great, and these can be loaded externally from a file, as I mentioned already. So they can also be generated on the fly, which makes them incredibly powerful. So let's begin, shall we? So the first thing to do is to create a new function. This will take our program handle, shader source, and the type. So we start the process of setting up our shaders by creating a program object, which we will link to the shaders together into this object. Or sorry, no, this is the shader object. So if it wasn't able to create an object, then something went terribly wrong. So we'll print an error. And here we're going to do the magic of loading a shader. Now we specify the shader source for the object. The size, of course, and the lengths. Now we'll compile the shader. And now we will, very simple, make sure we include Sterling here. Nothing to it. Now we're going to check to make sure it actually compiled. So we tested and it didn't work. So we're going to get a log. Get shader info log object 1024 bytes. No. And then now we're going to attach the shader to our shader program. So that's our basic little thing. Compiling the shader is very easy. After we have that all done, we're going to need a way to compile all the shaders. So let's begin this, shall we? So now we're actually going to create the shader program. So this is actually where we start the process of setting up our shader by creating our program object. And we will link them into this using this fancy little function we used here. For some reason, oh, it's not Sterling, it's string. I'm a little tired. Should probably take a nap here. On our object. Oh, P. Now we have them. If it was unable to create a program, then we'll do the same thing. We'll printf exit blah blah blah, and then now we can actually now we're actually going to be able to create some shaders. So I'm going to put them here: static constant char star render shader vertex. For now, it's going to equal nothing. Constant char render shader fragment shader, also going to equal nothing for now. So there we have it. Now we're going to actually attach these. So there's our program, proj. Our shader is going to be render shader vertex shader, and this will be GL vertex shader. So that will do the one bit. This will do the other. And then finally, we have to do our big test, and that can be done with test equals 0 GL. So now we'll actually do all the work right here. So after compiling all the shader objects and attaching them to the program, we can finally link it. Note that after linking the program, you can get rid of the intermediate shader objects by calling GL delete shader for each and every one of them. So now we're going to check to make sure that any program-related errors, such as link errors, a bit differently than shader-related errors. Instead, we have to get shader IV. Instead of get shader IV, we use get program IV, and instead of get shader info log, we use get program info log. Just gonna throw out the log. This should be a glint. And then now we're going to validate that the program. Now we have to validate the program. I'll explain what that does after I write it. So you may be asking yourself why we need to validate a program after it's been successfully linked. The difference is that linking checks for errors based on the combination of shaders, while the call above checks whether the program can execute given the current pipeline state. In a complex application with multiple shaders and lots of state changes, it's better to validate before every draw call. In our simple application here, we check it just once. Also, you may want to do this check only during development and avoid this overhead in the final product. Finally, to use the link shader program, you set it into the pipeline state using the call above. This program will stay in effect for all draw calls until you replace it with another or explicitly disable its use and enable the fixed function pipeline. By calling GLUse program with null, if you created a shader that contains only one type of shader, then the other stages operate using their default fixed function pipeline functionality. We have completed all the OpenGL preparation for this. Now begins the actual stage of initializing the shaders, which can be done after render prepare. And now we are actually going to write our first vertex shader. You ready? So I'm doing this as a character constant. So version 330 here tells the compiler that we're targeting version 3.3 of GLSL. Actually, I wonder if I can define raw. Oh, this is the only problem. We're going to throw this in here because it's a directive, and then we'll just concatenate it with that. So start out with the first one. So this statement appears in the vertex shader. It declares that a vertex-specific attribute, which is a vector of 3 floats, will be known as position in the shader. Vertex-specific means that for every invocation of the shader in the GPU, the value of a new vertex from the buffer will be supplied. The first section of the statement, layout location equals 0, creates the binding between the attribute name and the attribute in the buffer. This is required for cases where a vertex contains several attributes, position, normal, texture coordinates, etc. We have to let the compiler know which attribute in the vertex is the buffer. In the buffer must be mapped to the declared attribute in the shader. There are two ways to do this. We can either set it explicitly as we do here to 0, in the case that we use a hard-coded value in our application, which we did with the first parameter of the call GL vertex attribute pointer, or we can leave it out and simply declare it in vec3 position in the shader, and then query the location from the application at runtime using GL get attribute location. In that case, we will need to supply the return value to GL vertex attribute pointer instead of using the hard-coded value. We chose the simple way here, but for more complex applications, it's better to let the compiler determine the attribute indices and query them during runtime. This makes it easier integrating shaders from multiple sources without adapting them to your buffer layout. You can create your shader by linking together multiple shader objects. However, there can only be one main function for each shader stage: vertex shader, geometry shader, fragment shader, which is used as the entry point to the shader. For example, you can create a lighting library with several functions and link it with your shader, provided that none of the functions there is named main. Here we do hard-coded transformations to the incoming vertex position. We cut the x and y values by half and leave the z unchanged. GL position is a special built-in variable that is supposed to contain the homogeneous, containing x, y, z, and w components, vertex position. The raster visor will look for that variable and will use it as the position in screen space, following few more transformations. Cutting the x and y values by half means that we will see a triangle which is 1/4 the size of the triangle in the previous tutorial. Note that we are only setting w to 1.0. This is extremely important to get the triangle displayed correctly. Getting the projection from 3D to 2D is actually accomplished in two separate stages. First, First you need to multiply all your vertices by the projection matrix, which we will develop in a few tutorials, and then the GPU will automatically performs what is known as a perspective divide to the position attribute before it reaches the rasterizer. This means that it divides all the components of the GL position by the W component. In this tutorial, we are not yet doing any projection in the vertex shader, but the perspective divide stage is something that we cannot disable. Whatever GL position value we output from the vertex shader will be divided by the hardware using its W component. We need to remember that or else we will not get the results we expect. In order to circumvent the effect of perspective divide, we set W to 1.0. Division by 1.0 will not affect the other components of the position vector, which will stay inside our normalized box. If everything worked out correctly, 3 vertices with the values minus 0.5, minus 0.5, 0.5, minus 0.5, and 0, 0.5 reach the rasterizer. The clipper doesn't need to do anything because all the vertices are well inside the normalized box. These values are mapped to screen space coordinates, and the rasterizer starts running over all the points that are inside the triangle. For each point, the fragment shader is executed. The following shader code is taken from the fragment shader, which we will develop now. So the first line here, usually the job of the fragment shader is to determine the color of the fragment pixel. In addition, the fragment shader can discard the pixel altogether or change its Z value, which will affect the result of the subsequent Z test. Outputting the color is done by declaring the above variable, the 4 components R, G, B, and A for alpha. The value that you set into this variable will be received by the rasterizer and eventually written to the frame buffer. The following line here in our main function. So here we set the frag color to red, as in red, green, blue, alpha, we're setting it to red. So if we compile this, technically we should have a quarter-sized red triangle. Care to give it a go? Congratulations, this is the end of tutorial 4. It's a scaled triangle, precisely a quarter of the size, and it's red. Exactly what was intended. That's all for this tutorial, and sorry for it taking so long. It is actually quite a lot of work explaining the basis of shaders, but wait until you see the next tutorials, which we are going to describe transformation, rotation, all of which are incredibly more complicated and require a little more knowledge of mathematics, which thankfully I will describe. This is the end of the tutorial. Stay tuned for more.